Hi, everyone, and welcome to episode 33 of Diabetics for Diabetics Radio. I am your host, Bowie, and today's episode is titled Iron, the Inflammatory Super Spreader. We're going to talk about some of the cellular mechanisms in place that allow for excess iron, free iron in the cell, to cause otherwise mundane cellular functions to become toxic. And this plays a pivotal part in oxidative stress, and more specifically, oxidative stress in beta cells, which, as someone with type 1 diabetes, I am particularly interested in. If we have not met, my name is Bowie. I've had type 1 diabetes for over 22 years. I have started this healing journey about 2 years ago. I got really interested in kind of reinvigorating my interest in looking for more on the diabetes front. From both a research standpoint, what do we know, as well as what can I do about it? Because for the longest time, it was just kind of like I was taking orders from doctors and no new information. I wasn't happy with the progress, so I decided to branch out on my own. And that is how we are here. So I share a lot of short form content on TikTok. Go ahead and follow me there at Bowie_Madison. And subscribe here on the channel to stay up to date on what's going on in diabetes news. Now, let's go ahead and get started. So, one of the most important aspects that you have to know coming into this and seeing how iron uses ROS to make more ROS is understanding that reactive oxygen species are everywhere in the cell. And that's not necessarily a bad thing. So I've got there that quote, every action has an equal and opposite reaction. Every cell, every moment is creating energy of some sort, is going through some sort of biological process. All of those processes require energy. In the creation of energy, there is also going to be a creation of waste or a byproduct of that reaction. And ROS is the fundamental currency of basically cellular waste. It's telling the cell, hey, there's something here that needs to be taken out. Think of it like an office space. Throughout a typical workday, your waste paper basket is going to fill up with little odds and ends that you've accumulated throughout the day. Our immune system, our lymph system, everything that kind of keeps our cells clean, takes those on a moment-to-moment basis and disposes of them properly. It can be through, like I said, lymph, urine, feces. That's basically what our human excretion is all about. So, knowing this, and knowing that ROS are present in the cell to begin with at some fundamental low-level baseline way is important to know, okay? So ROS isn't bad. Our body has mechanisms in place to take care of them, right? And now you have to see now, what does that waste look like? Right? We've talked about ROS before. I think episode 10, 11, and 12 talk more about inflammation and how that works. But ROS, there's hydrogen peroxide, there's the superoxide anion, there's the hydroxyl radical. Okay, so what does ROS look like? Now, for most cells, the typical preferred ROS is going to be hydrogen peroxide, H2O2. You'll see hydrogen peroxide and H2O2 used interchangeably throughout the rest of the episode. They both mean hydrogen peroxide. Yes, it's the bubbly material that you put on wounds and watch it foam as it kills off all of the bacteria. But our body is incredible because, yes, hydrogen peroxide is a reactive oxygen species, which when we think of that, we think of oxidative stress and we think of inflammation. But hydrogen peroxide is the gentler version of ROS. So H2O2 is relatively stable, meaning that it's less likely to react with random things as it's being transported out of the cell. And because it is so structurally similar to water, H2O, H2O2, hydrogen peroxide is a lot more mobile. So it's going to be able to move through cell membranes and be passed out of the cell and into the waste system a lot easier because it looks a lot like water. And water obviously moves freely in and out of most cells. So this is kind of like the perfect way to package cellular trash because it's not going to cause any harm, right? It's like the equivalent of, you've got like a disposable bag in your trash can. That way you can kind of wrap it up, prevent any spills, give it to the trash man, like you see here, and it can be taken care of responsibly. Now, the next thing to see is that, we'll go back. Okay, so the next thing to think about is that, so cells and cell parts that make energy are going to make waste. That's how it works. You can't create something without having some sort of byproduct. So when you think of the mitochondria in cells, mitochondria is the site of cellular respiration. It's where glucose is made into ATP. It's basically what's fueling our cells, right? So with this high energy organelle, the mitochondria, with that high energy also means that it's going to have a lot of waste, okay? And like we said, that's not inherently a bad thing. Most mitochondria have the tools in place to neutralize the waste that they're producing, okay? So all cells create ROS. The more energy that's being created, the more waste byproducts that there are going to be. The mitochondria is one of those places where there's a lot of energy being created and a lot of waste. Now, put that in the context of beta cells. Okay, beta cells are incredibly metabolically active. They have to be. In a healthy body, they have to be. Every time you are eating food, your beta cells have got to turn on the gas all the way up to make sure that it is creating enough insulin to keep your blood sugar regulated and to make sure that your cells have the glucose available to oxidize and make ATP, right? So those are it's just a necessary evil, right? If you're going to be a high metabolic cell, you're going to have a lot of waste. Now, beta cells have some adaptations in place to handle those energy demands and waste products. Of course, it's not going to be, it's not going to be given more than it can chew, right? So we've talked about how iron plays a role in the beta cells, how iron plays a role in the mitochondria. Iron is a very, very important catalyst in the conversion of glucose to ATP, right? So mitochondria are energy rich. Anywhere where there's energy, there's going to be a lot of iron, ironically, pun intended. So mitochondria, energy rich. If they're creating energy, they also have to be iron rich. If they're creating a lot of energy, they also have to be very ROS rich. So beta cells themselves, because of how metabolically active they are, they have very active mitochondria. The beta cells themselves are unique among the pancreatic cell types in that they have a special protein called hepcidin, which is responsible for regulating and modulating iron retention and release within the cell, which would make sense because when we eat and take in food, that's energy coming in. That's letting the beta cells know, hey, we need to make sure that you can make insulin. And the beta cell is like, okay, well, if I'm going to make insulin, I got to make sure the body has enough iron. So I'm going to use, that has a unique relationship with both iron retention and release, as well as releasing insulin. Those two things kind of go hand in hand. Additionally, the endoplasmic reticulum, or ER, of beta cells is uniquely larger than in most cells. I think the size was somewhere about 14% of the cell mass was just one organelle, which is unusually high. But what this endoplasmic reticulum does for the beta cells is that it is basically like a bigger holding cell or trash can for a lot of those hydrogen peroxide ROS that are being let off by the mitochondria. But overall, the general idea is that it is a high energy cell creating a lot of waste. And it has these unique safety mechanisms in place to account for these high energy, high waste demands. So let's take, because the beta cells are unique in that they are so metabolically active and they require these unique handling strategies to handle all of this load, it's important to see all of the different parts of the beta cell that are making ROS. So we've got four here. We've got the peroxisome in the top left. Peroxisomes are a organelle specifically designed in not just beta cells, in a lot of cells, to oxidize and neutralize free radicals, right? So it's taking things that could potentially be dangerous and makes them less dangerous. It's part of digestion, right? If you're digesting food, if your cell's using energy, it's kind of like a place where waste can go to be neutralized. Either way, it's a place where there's going to be a lot of ROS. Peroxisomes specifically are involved in beta oxidation of free fatty acids, or the fats that we're eating and the cell is using. So peroxisomes are creating that hydrogen peroxide. We mentioned before mitochondria, clearly very, very energy dense, therefore creating ROS. So what I want to pay attention to here is that this arrow here, this MNSOD, okay? So through the process of cellular respiration, there's a couple different ROS being made. Superoxide anion is one of those ROS. But like we mentioned before, hydrogen peroxide is the preferred ROS because of how stable it is. So our body has an enzyme in place called manganese superoxide dismutase. And so this SOD, this superoxide dismutase, is something that takes that superoxide anion and turns it into hydrogen peroxide. Okay, so it's making a less stable ROS into something more stable that it is able to neutralize via this GPX enzyme, turning it into water and oxygen, which is something that is not toxic to the cell. Now, the endoplasmic reticulum is also creating its own free radicals. I mentioned before that the endoplasmic reticulum in the beta cell is larger because of that high hydrogen peroxide content, because of how active these mitochondria are. So they themselves are metabolizing hydrogen peroxide, as well as in the cytoplasm, the cytosol itself, just within the cell without actually being inside an organelle. Any superoxide anions that are byproducts of other cellular events happening in the cytoplasm are reacting with a different SOD. Notice how superoxide dismutase, that's something that's taking that superoxide, turning it into hydrogen peroxide, except this one is a copper, that's what Cu stands for, and zinc SOD. So just between the mitochondria and the cytosol here, notice how available and, well, how apparent trace minerals are, right? Manganese, copper, and zinc. Those are all things that you recognize from, nutrient labels and nutrition labels, right? So our body is using those trace minerals that we ingest from food and using it to neutralize oxide, the superoxide ions, into hydrogen peroxide. Now, the real important part about this and where toxicity comes in is the fact that when that superoxide ion is converted into hydrogen peroxide, this hydrogen peroxide is liable to react if there is free iron present via the Fenton reaction, which we have talked about extensively on this podcast, right? Hydrogen peroxide and iron is like a match to dynamite. It is something that makes it so much more toxic, right? So this OH dot here that you see in the mitochondria as well as in the cytosol, that is the hydroxyl radical. That is the Tasmanian devil version of ROS. It is so destructive. It just blows up in place. Your body cannot react quick enough to neutralize the damage, which is extensive, that hydroxyl radical can do. And because the mitochondria is a place where a lot of energy, a lot of waste, and a lot of iron is coexisting, it makes for some precarious situations, especially if you do not have the correct systems in place to neutralize those very toxic components, right? So the mitochondria, high energy, or beta cells in general, not just mitochondria, beta cells in general, high energy cell, creating a lot of waste. That high energy requires a lot of iron to convert to make this energy. A lot of that waste means a lot of ROS. So you have a lot of iron and you have a lot of ROS. Can we see the potential for danger here? Can we see the potential for disaster when you have this iron and this ROS, when we know that those two are the ingredients for creating the hydroxyl radical? And so here we are. Check episode 11 and 12. I've gone into this more extensively before, but the Fenton reaction is essentially where free iron is reacting with hydrogen peroxide here and creating the hydroxyl radical, multiple hydroxyl radicals, 2 to be specific, but it's essentially compounding what was once a stable ROS that could be readily removed from the cell and has turned it into 2 highly destructive, highly reactive molecules. Bad news for a cell. Bad news. Okay. So plenty of documentation on how destructive hydroxyl radicals are. Plenty of research going into the Fenton reaction. It's not just a bodily event. It's used commercially, industrially. It is an explosive type of reaction, and it has a very well documented bodily harm. Bodily harm like DNA and RNA deconstruction, mutations. It breaks up and destabilizes cell membranes. It tears apart proteins, enzymes, and it is, I'm trying to think of the right word for it. Nondescript. It is indiscriminate. Just indiscriminate destruction. Okay? Anything in its place, it's getting rid of. So when you think of ways that this could materialize in the state of diabetes, we have our beta cells with a lot of iron, a lot of ROS, and when we're diagnosed with diabetes, we're kind of like entering the crime scene and everything's kind of destroyed. Meanwhile, no one is looking to check for the hydroxyl radicals' fingerprints when logic would tell you that they have been there. Now, you would think, well, Bowie, why doesn't everyone have diabetes then? What is the thing that makes a diabetic's beta cells more susceptible than the next guy? So surprisingly, there's something going on where the beta cells of those with diabetes, well, beta cells in general, don't have high levels of enzymes responsible for buffering hydrogen peroxide. Or have they been compromised? Right? So part of the name of the game is twofold. It's you need to quickly neutralize the hydrogen peroxide to prevent it from degrading into hydroxyl radicals, as well as making sure that there isn't too much iron, free iron available to react with that hydrogen peroxide and devolve into the hydroxyl radical. Okay? So that's one thing. Like, you can see someone like, okay, why isn't everybody diabetic then? If you have these kind of two volatile components happening at the same time. So in the diabetic state, you have to ask, well, what has been compromised so that either A, there's an abundance of iron accumulating, or we don't have enough stuff to buffer the hydrogen peroxide. And so these are just three examples. There's more of them, but these are three enzymes within the cell that are known to buffer ROS accumulation. Glutathione peroxidase, hydroperoxide glutathione peroxidase. There's a whole slew of that GPX enzymes. There's GPX1, X2, X3, X4, as well as glutathione itself, which, if you're into supplements, you know that glutathione can be supplemented. But glutathione is a naturally occurring antioxidant in the body. And specifically for beta cells, glutathione is the tool of choice for neutralizing the hydrogen peroxide. Question remains, why do diabetics have low glutathione? Is it a game of, are we producing too much hydrogen peroxide, or is it a game of we don't have enough to buffer the hydrogen peroxide we have? It's probably a combination of the two, if you ask me, but that's what's going on. And so I've made a few TikTok videos recently about Sigurd Lenzen, who is the author here that I'm citing from his 2017 paper. And he has honed in on the specifics of beta cell ROS generation and buffering, and what parts of the cell are having trouble dealing with that ROS. So let's walk through this paragraph here. So at the top, in view of the low expression level of GPX1, which is the glutathione peroxidase. This is something that buffers hydrogen peroxide. So in view of the low expression of GPX1, in particular the beta cell mitochondria. So the mitochondria is low on this buffer for ROS, not a good sign. The regenerative reduction of oxidized glutathione achieved through glutathione reductase is crucial to avoid an overpowering of the limited antioxidative defense capacity. Okay, let that sink in for a second. We have mechanisms in place that are regenerating glutathione in order to keep up with this hydrogen peroxide creation. That is achieved through glutathione reductase. Okay, so that's just one of the enzymes that is going to basically repurpose glutathione to be used again. So this maximizes the chances for beta cell survival in situations of mitochondrial stress. Mitochondrial stress just means more ROS that needs to be handled by the glutathione. This necessity is supported by experimental evidence provided by studies in different animal models of diabetes. So in this DBA2 mouse model is a particular breed of diabetic mice. Now, this is a constitutive overexpression of manganese superoxide dismutase, which, if you'll remember, is the molecule responsible in mitochondria for converting superoxide into hydrogen peroxide. So let's take a second here. Do you remember this guy right here in the mitochondria? Superoxide, manganese, SOD, turns it into hydrogen peroxide. So this one particular paper, or this one particular reference here, is saying that they made a mitochondria in a diabetic mouse that made too much hydrogen peroxide. Okay. And this creation, when they made that enzyme that made too much hydrogen peroxide, it led to beta cell dysfunction. Okay, so we have some fingerprints there on what's causing this beta cell dysfunction. It's that overabundance of ROS. Now, below that, in the these are just different mouse breeds signifying the diabetic model. There's also another enzyme, nicotinamide nucleotide transhydrogenase. There's not a quiz at the end of this episode. It's just an enzyme. Prevents the prompt generation of GSH. GSH is glutathione. Okay, so in this mouse model, they took away the enzyme that helps make glutathione. And if you don't have glutathione, you can't buffer hydrogen peroxide. This showed an instantaneous regeneration of glutathione is mandatory to maintain protection of beta cell mitochondria, right? So they had this cell, they wiped out its ability to recreate glutathione, beta cell dysfunction. So again, more mechanisms, right? We've got too much ROS. If you introduce too much ROS, beta cell dysfunctions. If you take away the cell's ability to manage ROS, beta cell dysfunction. Okay. So let's do some speculation on our part. Okay, so think about this. In someone with diabetes state, they have, over multiple generations, they've been overstimulating their mitochondria, therefore creating a lot of waste, right? This could be overconsumption calorically, just in general, of food, but the processed sugar and those easily oxidized fatty acids, components of basically the standard American diet or the standard Western diet, where high energy creating a lot of waste. So our metabolism has been under a lot of stress for a long time. Combine that with poor activation of the enzymes needed to buffer the ROS. Remember, manganese, SOD, copper, and zinc, SOD, those are the enzymes responsible for creating hydrogen peroxide and neutralizing, like having that have someplace to go. So if we don't have those trace mineral components to allow those enzymes to do what they need to do, we're accumulating more ROS and not neutralizing them. Combine that with an overabundance of inflammatory amplifiers, iron specifically. I have focused solely on iron in my studies, but iron is in the cell in overabundance. We have more iron than we know how to package and we know how to get rid of. So it's floating freely in too many cells. It's floating freely in cells that are unable to handle the ROS that is accumulating in those cells. So you've got too much ROS and too much iron. The Fenton reaction, we are creating so many hydroxyl radicals, the cell is just overrun with oxidative stress. So let's walk through it. Beta cells, always on. Now, they're always on, for anyone that eats daily, right? That's kind of like a human thing. But typically in a healthy diet, you are eating nutrient-dense food that is yes, asking the cell to create energy, but it's also creating, or it's also supplying the resources the cell needs to get rid of the garbage that's accumulating because of that energy creation. So beta cells activated to the max all the time, creating unusual amounts of ROS because our foods have been modified in a way that we are just overridden with, processed carbs, processed foods, enriched foods, what have you. Meanwhile, they've been processed with all of those accelerants, and they've had the nutrients, the tools, the plant compounds removed so that we're creating a lot of waste, and we don't have anything in place to neutralize the waste. So you've got too much garbage accumulating. Think of it like a hoarder's house. You've got too much garbage accumulating, and now there's iron hanging around because not only were those essential trace minerals removed from the processed food, we added gasoline to it by adding extra iron. If you check any enriched wheat flour, any processed good, chances are it's going to have reduced iron added to it. That is the match being lit and thrown into your beta cells, high ROS loaded cells. And that's where this Sigurd Lenzen author and his colleagues here are talking about how hydrogen peroxide, which again is a typical byproduct in the cell at correct levels, but it can also work against us. Its stability can work against us in a cell that has too much iron. So this is all from the abstract, but let's read through it. So the toxic potential of hydrogen peroxide is limited, even if intracellular concentrations of peroxide increase, right? Hydrogen peroxide is less reactive, not something to be typically worried about because our cell kind of is familiar with that, with how much energy it creates. Its toxicity is mostly restricted to the oxidation of a few thiol groups, which is, at really, really high levels with some very specific types of materials, it can be destructive, but typically not. However, the hydroxyl radical, the OH radical, is generated spontaneously from H2O2 in the Fenton reaction. The hydroxyl radical is extremely toxic and destroys any biological structure. Due to this high reactivity, its action is limited to a locally restricted site of its generation. So, whereas the H2O2 is the preferential mode of ROS because it's stable, it moves freely, it can kind of be disposed of without blowing up in anyone's face. Once it turns into hydroxyl radical, it's blowing up in people's faces, okay? So due to the high reactivity of hydrogen peroxide with iron, H2O2 can serve as a super spreader. So see here with the hydroxyl radical, due to the high reactivity, its action is limited to a locally restricted site of its generation. Wherever the hydroxyl radical gets created, that's where the damage occurs. It's not traveling anywhere in the cell. As soon as it is there, it's reacting with something. Whereas hydrogen peroxide, it can be created and moved freely so that it can be disposed of without blowing up like the hydroxyl radical does. So on the other hand, hydrogen peroxide, with its stability and long half-life, can reach virtually any site in the cell and distribute its toxic effect throughout. So this hydrogen peroxide, because it can move freely throughout the cell, is moving freely throughout the cell, happening upon free iron, where, it's kind of like just going about its merry way. It's in the trash can, ready to be disposed of. If it meets free iron anywhere else throughout there, it's creating the hydroxyl radical and instantly imploding and creating destruction. Here's a continuation of that abstract. So in the scenario, hydrogen peroxide is the pro-radical, right? Kind of like not awful, but has the potential to be awful with the right ingredients. that spreads the toxic action of the hydroxyl radical. It is the longevity of the peroxide molecule, allowing it to distribute its toxic action from the site of origin all over the cell, and may even mediate intercellular communication. Those hydroxyl radicals, like I said, are indiscriminate. They are, whatever is in their path, they are destroying. This can affect more than just the cell it's in, if it's allowed to destruct enough of that cell. Thus, peroxide acts as a spreader by transporting it to sites where the extremely short-lived hydroxyl radical can arise in the presence of free iron. So free iron is the catalyst that is converting hydrogen peroxide to hydroxyl. So peroxide and the hydroxyl act in concert due to their different complementary chemical properties. They are dependent upon each other while executing the toxic effects in oxidative stress under diabetic metabolic conditions, in particular in the highly vulnerable pancreatic beta cell, because we talked about how high energy it is, how high waste it is, and how high iron it is. And because of those things, it does not have the typical regulatory proteins in place to neutralize all of this ROS. Dangerous, very dangerous. This highly mobile and abundant ROS, H2O2, is reacting with a highly supplemented, knowingly or not, where we're eating iron in regular food, and then with processed and enriched food, it's making more iron available to create a more destructive, poorly defended against hydroxyl radical. Boom goes the dynamite. So where do we go from here? How do we address these situations, right? We talked about how trace minerals are important for getting the enzymes responsible for neutralizing hydrogen peroxide to work. Simultaneously, we've got an overabundance of iron, which is like the match lighting all of this on fire. So twofold: decreasing mitochondrial stimulation, over-consuming high-calorie, nutrient-poor foods, right? If you are eating out of a box, if any of your food is processed or enriched, that processing and that enrichment typically comes in the form of imbalance and loading up on the bad, things like iron, and taking and stripping away the balancing trace minerals. So the more you eat these, the further skewed your imbalances are, the less of a buffer you have to protect against this accumulation of ROS. In addition, because this is systemic and has been happening over a long period of time, we've got a big buildup of iron in our bodies that is causing this spontaneous generation of all these hydroxyl radicals. So what I've been doing and what I've been focusing on is offloading iron, blood donations, natural iron chelators. I've talked about this in previous episodes as well. But we need to decrease the amount of free iron that hydrogen peroxide is just happening upon and imploding with, right? So increase the good trace minerals that boost enzyme activity to neutralize hydrogen peroxide. This specific example mentioned manganese, copper, and zinc. They are not the only three, but they are three that were mentioned by name in this particular paper. And you need to offload iron. I do it through blood donations. You can do it through natural iron chelators. A lot of the highly touted antioxidant supplements owe their antioxidant abilities to their ability to chelate iron. Berberine is one of them. Berberine chelates iron. Curcumin or turmeric chelates iron. So it's all about binding the reactive iron, allowing your body to get rid of it, and supplying the tools your body needs to neutralize the ROS that are resulting. That's my story, and I'm sticking to it. All right, so thank you all for being here. I'm so grateful to have the audience that I do. I'll have the citations and the resources that I used in this paper, or in this presentation rather, in the description. Check out more, learn more about what I'm reading on my website, bowiemadison.com. Follow me on TikTok and subscribe here on the channel. If you are someone with diabetes, responsible for someone with diabetes, or know someone with diabetes, send them this way. We are making a lot of really incredible progress, and it's not going to be something that you find in your endocrinologist's office. So with that, this is the end of episode 33 of Diabetics for Diabetics Radio. I'm your host, Bowie Madison. Thank you so much for being here, and enjoy the rest of your day.